At this point, you might be tempted to say, what is going on here? It seems that functions of the same shape, they just randomly seem to either have areas that are finite or infinite for no apparent reason. We've seen now two of these functions. So we've seen the function 1 over x cubed. When we integrate that from 1 to infinity, we got a finite number. Recall that we got here we got 1/2, and when we did the same thing with the integral of 1 over square root of x, in other words 1 over x to the 1/2, we ended up with infinity. Let me just try to suggest what's really going on here. If you look at these functions, 1 over root x and 1 over x cubed, first of all, they all have the point 1 comma 1 on them. In other words, 1, 1. And in fact, they cross the two functions. The red function is y equals 1 over x cubed. The purple one is y equals 1 over root x. They cross each other at the point 1, 1. Y equals 1 over root x, because the square root function tends to reduce it's smaller than x. In other words, square root of x for very large values of x, square root of x is going to be smaller than x, and for very large values of x, x cubed is going to be much larger than x. What that means is that for the purple function, the denominator is growing slowly, but for the red function, the denominator is growing very quickly. What that means is that the purple function is descending toward the x-axis, toward a value of y equals 0, but it's not doing it that quickly. On the other hand, the red function, you see that I'm tracing here, because the denominator is growing so fast, the red function is going to descend towards 0 very, very quickly. So the issue is that somehow the smallness of the y value in the red function overtakes the fact that we're extending the interval out to infinity because that function descends towards 0 so rapidly. For the purple function, since it doesn't descend towards 0 nearly as rapidly, the fact that the interval is infinite is able to overtake that function and cause the area to add up to an infinite number. That's kind of the intuitive understanding of what's going on. But the real key to understanding this is to recognize that somewhere in between the purple function and the red function, there must be a dividing line. There must be this green function, which I've written here as y equals 1 over question mark. We don't know what it is yet, where this is the dividing line between functions that descend quickly enough that their area adds up to 0, and functions that don't descend very quickly and their area comes out to infinity. This is where we enter what's called the p-integral. The p-integral is the integral from 1 to infinity of 1 over x to the p, where p is just any number. So p can be any number, but what we want to do is figure out if there's something we can say about p that will tell us whether this integral converges or not. So what we're going to do is we're going to integrate it. We're going to integrate this function for any value of p. And see what we get. So first thing we have to do is we actually have to do this in cases. We have to do the case where p is not equal to 1. Let's do this as case 1. And the reason for that is that recall that the integral of dx over x to the 1 had this special rule. So we were able to deal with, for any value of p that isn't 1, we can integrate this through the power rule, but if p is equal to 1, we have to integrate it with the special rule that tells us that integral is the natural log function. So we'll handle that one a little bit later. Let's just look at case 1 where p is not equal to 1. So we're going to write the integral from 1 to infinity of x to the p, sorry, not x to the p, of dx over x to the p is equal to the limit as b approaches infinity of the integral of x to the negative p dx from 1 to b. That equals the limit as b approaches infinity of, if we add 1 to negative p, we get x to the negative p plus 1, which we'll write as 1 minus p. That's x to the 1 minus p, and then we divide by the exponent, so 1 minus p. This can actually be written maybe a little bit, it becomes a little easier to see what we're doing. I'm not going to say that it's always better to write things in one form or the other, it's just that this form is going to help us to see what we're doing. If I write this as 1 over 1 minus p, x to the p minus 1. In other words, all I'm saying here is that x to the negative 5 is equal to 1 over x to the 5, right? So I can just multiply this exponent by negative 1 and put it in the denominator. That's what I did there. So, and this is going to go from 1 to b. So this is going to be 1 over 1 minus p, sorry, I need the limit. This is going to be the limit as b approaches infinity of 1 over 1 minus p. I can take that factor out and go 1 over b to the p minus 1 minus 1 over 1. Now, the issue is going to be, when is this expression infinite and when is it not infinite? So it's going to turn out that this expression will evaluate to 0 as long as I'm raising b to a positive power. If you think about it, the limit as I'm going to put this in terms of x approaches infinity, of 1 over x to the point 0.00001 is equal to 0. So in other words, if I'm taking an infinite number in the denominator and raising it to any positive power, eventually that denominator is going to become infinity and it will go to 0. On the other hand, the limit as x approaches infinity of 1 over x to the negative 0.001, I'll just put in a little bit, that's going to equal the limit as x approaches infinity of x to the 0.001. In other words, I take it out of the denominator, but I take the negative sign out. So now I'm taking infinity and raising it to a very small number, but this is still going to equal infinity. So it turns out that this is the dividing line. In other words, let's just write this here. 1 over b to the p minus 1, sorry, the limit as b approaches infinity of 1 over b to the p minus 1 is equal to 0 if p minus 1 is greater than 0, and infinity if p minus 1 is less than 0. In other words, if p is greater than 1 or if p is less than 1. And of course, we don't have to deal with the p equals 1 case because we already restricted ourselves to p not equal to 1 for reasons that we discussed. So going back to this expression, that means that, I just want to bring that down. In other words, this was kind of an aside. This is going to equal 1 over 1 minus p times 0 minus 1, which equals 1 over, this is going to confuse some people if I don't do the step, 1 over 1 minus p, which equals 1 over p minus 1. In other words, as long as if p is greater than 1, and it equals 1 over 1 minus p times infinity minus 1, which equals infinity if p is less than 1. So, in other words, if p is greater than 1, we get a finite number. If p is less than 1, then we get infinity. That turns out is the dividing line. It turns out that the p integral is going to converge as long as p is greater than 1, and it will diverge if p is less than 1. We just have to do the case where p equals 1, and that's going to turn out to be relatively simple. Case where p equals 1. So we're going to call this case 2, actually, where p equals 1. So here we're just integrating from 1 to infinity the integral of dx over x, because that's the case where p equals 1. That equals the natural log of x. Well, actually, let me do this formally. This is the limit as b approaches infinity of the integral from 1 to b of dx over x. That equals the limit as b approaches infinity of ln x going from 1 to b. So that equals the limit as b approaches infinity of ln b. I can take the absolute value out because infinity is a very large positive number anyway, minus ln 1. Using the law of logarithms, that equals the limit as b approaches infinity of ln of b over 1, which is just b. And that equals infinity. I know that many of you know that the log function looks like this and think that it must approach an asymptote, but it doesn't actually. The log function, y equals ln x, just keeps growing and growing and growing just very, very slowly. So it looks like it's asymptotic, but it actually, give it enough time, let it go to the right as far as you want, and it will become infinite. So to sum up, what we have is that the integral from 1 to infinity of dx over x to the p is equal to 1 over p minus 1 if p is greater than 1, and it diverges if p is less than or equal to 1. This is the rule for p integrals. So as soon as an integral has this form, we know that it either converges. We'll write up here, by the way, that this is, in the case of p greater than 1, the integral does converge. Usually we don't care so much that it equals 1 over p minus 1. The only reason that we care about this is that 1 over p minus 1 is actually a number. Usually we're only interested in the question of whether the integral converges or diverges. So the important point here is that if p is greater than 1, then the integral converges. Otherwise, the p integral converges. Otherwise, if p is less than or equal to 1, the p integral diverges. And I'll just write here, this is the p integral rule for p integrals on the interval 1 to infinity. So to test your knowledge of p integrals, I invite you to consider which of the following integrals that you see here, a, b, and c, which ones converge, and which ones diverge. Let's look at them one by one. So first of all, in integral a, we have 1 over x to the 1.000001. This is a p integral with p equal to 1.000001, which we note, even though it's very slightly so, it is greater than 1. Therefore, we can say that the answer is that a converges. It doesn't matter how little the exponent exceeds 1 by. As long as it exceeds 1, the integral converges. Now, for b, we're taking the same integral, but we're multiplying it by the number 20 billion. Surely, if I take this integral and multiply it by 20 billion, surely that must make it go out to infinity. But it doesn't, because what this is this is just going to be 20 billion times some finite number. It's 20 billion. This is the time symbol, not an x. 20 billion times a finite number, which still equals a finite number. In other words, if I simply take this 20 billion and put it outside the integral, what I have is an integral that comes out to a finite number. I multiply it by 20 billion, and I get another finite number. So the answer is that b converges. So a converges and b converges. Now, what about c? C, we're taking the integral of 1 over x to the point 9999997, and we're multiplying it by, I forgot the dx. Of course you're going to say this diverges because I didn't say that there was a dx there. So what we're doing is we're taking this integral and multiplying it by an unimaginably small number. We're taking 100 million zeros. This is going to be 0.00 dot 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 01, where here we have 100 million zeros before we get to the 1, and then for good measure we're also going to multiply it by 0.000001, thereby adding another 7 zeros, because that's going to make a difference. So we have 100 million and 7 zeros before we get to the 1, and then we're going to multiply that by the integral of 1 over x to the point 9999997. But even if we take this unimaginably small number and multiply it by infinity, we still get infinity. So it doesn't matter what we multiply a p integral by. The only thing that's going to matter is the p format itself. This is x to the 0.9999997, which here we have p equals 0.9999997, which is less than or equal to 1. So the answer is that the integral diverges.